All right, line A6, learning test 6. We're going to take a look at features of our specialty thyristors. So far we have covered inside of third year here the SCR and the FETs, the IGBT, and then my triacs. And so now we're just going to get into a couple smaller ones that are generally used more as control components. And these are going to go and be our Diac, our UJT, or unijunction transistor, and our LASCR, or light activated SCR. We're going to start with the Diac. The Diac is a bidirectional component. It means Diac itself is a bidirectional diode thyristor, and it can also be referred to as bilateral trigger diode. What we'll use them for is we are going to go and use these as a breakover point that we can then use to go and trigger something else, because each of these is going to go and have a voltage rating. Whatever that voltage rating is going to go and be, this thing can go and break over, go into conduction when it sees that across from terminal 1 to terminal 2. The voltage itself is going to go and be called the VBO, voltage breakover, that this thing will go and turn on with. And it gives us a graph that looks something like this. It can operate inside of, if I take a look at it, quadrants 1 and quadrants 3 over here, which means that I can use it to drive current out in the forward direction. I can run something in the forward direction, forward voltage, forward current, or I can run something in the reverse direction, reverse voltage, reverse current. If I take a look at the characteristics, I see that as I increase my voltage, this is my voltage going up over here, I'm seeing only a tiny rise in the amount of current, right? Here's the current, it's kind of just rising a tiny little bit. And this region all over here is going to go and be leakage current. It's a solid state device, there's always going to go and be some leakage that's going to happen inside of it. But then I get up to this point that I hit my forward breakover voltage, my positive VBO, and once I hit that forward breakover voltage, all of a sudden, this thing is going to start to rapidly rise in its value of current. You'll see that the voltage backs off on it as well because it's been acting as a open switch, a high amount of resistance, and then all of a sudden when this thing goes into breakover, the resistance of the device itself is going to be dropping. And because it's dropping its resistance, V is equal to I times R. Because the resistance is dropping, the voltage that is going to be seen across the device is dropping as well. That's where we get this little weird backwards knee over here. But what we're seeing is not so much that we want to examine the knee, we want to examine the fact that this is current moving in a upward direction, a more positive direction. And we see that this thing is then able to go and conduct current in that same positive direction. There's more current that's going on inside of it. Okay, so that's our schematics that we have for these ones. Going back to the actual, what the symbols are for these, it looks like a set of back-to-back diodes, and these are going to be back-to-back diodes that are associated with a specific value of voltage. We will buy these at the voltage that we are trying to go and take these things, have them operate at, breakover, etc. They're going to be chosen by the manufacturer. There is no third terminal off of these. We've only got main terminal 1 and main terminal 2. The third terminal that we have seen off of our Triac and our SCR that's going to be a control terminal just doesn't exist. These are simply going to be controlled by my volts, the breakover volts. The amount of current that they're going to be able to carry is generally speaking going to be very small. They're a control device, not a massive amount of current that we're going to go and carry through. We don't use them to drive the actual loads themselves. And so as a result, they're going to be relatively small. They show a couple of small cases over here, like this first one here, the DO7, that's like a standard small resistor size. This other one here, the DO92, is probably maybe about the size of a little pink eraser on the top of a pencil or something like that. Relatively tiny little devices that we are going to go and have. We'll use them for controls, not for bulk power. And if I take a look at this, it shows me the total amount of power that I can dissipate off of, this is a sample one, is going to be rated in the milliwatts. These aren't full watts, these are milliwatts. We're looking at about 1/4 of a watt, or a relatively small amount of current that we can go and have. Okay, usage of them. Most common place that we're going to go and see these utilized is going to be inside of what we refer to as a oscillator type of circuit. And an oscillator circuit is something that's just going to go and move back and forth. And for our purposes, it's going to be an up-down type of circuit. If I take a look at this, I see that I have got DC positive and I have got a negative over there. I also see that I have got a variable resistor and I have got a capacitor. You should be quite familiar with this setup by now. You've seen it inside of second year, you've seen it now inside of third year as well. But anytime that we see a RC together, it's going to be a timing thing. Basically, we are looking at the amount of time that it's going to go and take to charge the cap will be determined by the amount of resistance we put into it. Lots of resistance, slow build on the cap, little resistance, fast build on the cap. And we're using that voltage across the cap over here to go and fire our diac that we are going to go and have. My cat is just sitting almost over top of the microphone sneezing right now, so just disregard him. All right, let's go and take a look at how this thing operates. We're going to start with this thing at a high value of resistance. So we'll just say the resistance is at a high value. If resistance is at a high value, what's going to happen is we have got a negative over here. This thing has not broken over yet, so we're going to go and say that this thing is sitting as if it were an open switch that we are going to go and have. So it's not doing anything right now. Electrons are going to start to build up here on this plate. For every action, there's an equal and opposite reaction as other electrons are driven away from here and they are traveling through here out to my positive. So I'm going to go and get a build. As I send electrons here and create holes, another electron, another hole, every time that this happens, my voltage is going to be seen as rising across here. So that's what I'm seeing on this first part over here. So my voltage is going to be rising. And my voltage is going to go and slow down as it rises. You should remember that it's got 5 tau to charge a capacitor in DC. You learned that inside the second year. And that it grows along this weird sort of curve. It's called the universal exponential curve that we have. So we see that universal exponential curve starting to grow over here. And then all of a sudden, something magical happens. The diac over here reaches its forward breakover voltage. And when my diac reaches its forward breakover voltage, it's as if we had a switch that was open here before that is now going to go and close. And so it's going to go and close. Now, I know that it looks like it's going to cross from the positive over to the negative. And that worries some of you because you think, oh no, have we just created a short circuit? We haven't created a short circuit because if I were to go and look at this as a closed switch, I would see that any current that would flow through it would have to go through it and through that resistor to get back out there. So it's still going to be a controlled amount of current. I'm not actually worried about this source current that's traveling through. There's going to be a tiny little bit of source current that's going through there. What I really want to go and take a look at is what this does over here. If I take a look at it, it's as if I took a switch and I closed it in parallel across this cap. Okay, that's all that this branch over here is a switch across the cap, which would mean that my electrons are going to be able to go and fill holes. That's what an electron wants to do. It just looks for the nearest orbital that it can go and fill that excess hole. And so what happens is this thing has closed because we hit the forward breakover volts, and as a result, all these electrons over just a split second, note there's no resistance in this here, all these electrons are going to go and flood back and fill these holes over here. And when that happens, it's going to go and cancel out a bunch of these, and we cancel out a bunch of these, and my voltage is going to go and drop. And it's going to drop really rapidly because there's no resistance inside of here. That's what we're seeing happens over here. What then happens is we are going to go and run off. You see that there's fewer electrons and fewer holes over here. Well, as a result of that, my IH, the holding current that my diac is going to go and have, and a diac does have holding current inside of it, the diac is going to go and lose that holding value of current. And as soon as it loses that, then this thing is going to go and shut off. So this switch over here is going to go back to being open. Boom, we lose that current path. We've dropped back down to a low value of voltage. This was the value of voltage where my holding current was going to be too small. And now this thing opens, which means that I'm going to go and continue to now rebuild electrons there, rebuild holes over here, and my voltage once again starts to go and rise. And so I'm going to start to go and rise up here. We hit the forward breakover. Once we hit the breakover, boom, it drops, discharges the cap. It hits the value of holding current there and rises again, boom, drops, etc. So we are going to go and have this drop that's going to go back and forth from one to the other. Now, you'll hear these things referred to as sawtooth generators, or sometimes people will call them triangular wave generators. A true triangular wave doesn't have the curve to it. But what we'll use this for is I can use this peak over here to go and trigger something else. We got a bunch of other components that need peaks to go and operate, right? We've got to go and have a gate. You guys remember these at this point. We're going to go and have our triac. I'll just draw a quick triac over here. and that triac is going to go and have a gate, and we have to go and have a little bit of a gate pulse. Well, if we go and build this circuit right, we can go and select correct values for this, correct values for my triac, so that anytime that it hits this peak, it's going to be enough power, my I gate and my E gate, to go and gate, this larger load carrying component over here, my triac itself. We can use them for SCRs as well. Now, what we have inside of here, you'll see, is a DC system. Okay, so this is just where I'm taking DC and I'm converting it over to a sawtooth DC type. It's not changing directions or anything like that. It's still always going to be in the positive region that I'm going to go and have over here. And if I adjust this resistance, if I increase the resistance, bring that up, it is going to take a longer time to charge up. And so we're going to go and have a lower frequency on our sawtooth. If I go and take my resistance and I drop it significantly, it's going to go and charge up really quick, drop, really quick, drop, really quick, drop, etc. So I'm able to go and adjust, just by using this rheostat over here, the amount of time that it's going to take for me to go and create that sawtooth, and really the frequency of my output waveform itself. All right, let's go take a look at these things now in AC. First of all, remember that the Diac is a bidirectional device, which means that it is going to be able to go and carry current in both directions, and we can use this thing fully inside of AC without having to do any rectification ahead of it. What we have over here is we have got a drawing showing us with a couple of components that you should be able to identify right off the bat. First of all, this guy over here is going to be your triac. So this is going to be able to carry large amounts of current. It's not as big as the SCR, but fairly large amounts of current. And we control it off of a gate. Then we see that we've got a diac, which is controlling the gate. And then we see that we have got a RC network over here, which is just going to be a way for me to control the amount of current that is going to go and reach this capacitor, which is going to allow me to control the amount of time. One other thing I want to just point out about this RC network is the fact that it's got two resistors over here. This is very commonly done when we are building industrial controls, because it's this thing that we call idiot proofing. Okay, customer malfunctions is the nicer way to write it up when you're filling out a work order. But a customer malfunction is really where somebody just does something and they wreck it, and we try to prevent that. And so what we'll do is, instead of having just a rheostat, if I only have a rheostat inside here, there's a chance that the customer could turn it all the way down to 0 ohms. And if they turn it all the way down to 0 ohms, we could get a ton of current that's going to flood through here, possibly blow this capacitor itself. So what we'll do is we will go and place another resistor in front of it. We'll just say this is a 100 ohm resistor in front of it. And by doing that, even if the customer adjusts this rheostat from 0 ohms all the way up to, let's say it's 10k ohms or something, they can adjust anywhere inside of that range, but they're never going to be able to drop it far enough that there's no resistance inside of here. It's just a really handy thing for us to go and have. So we'll see that commonly where we have a fixed resistor in line with the rheostat, so that the customer cannot go and drop below certain levels. We'll do that even in industrial controls. When you get into PLCs and things like that that are going to be control devices, sometimes you're going to go and use rheostats that are going to give you a 0 to 10 volt signal back, or you can be running a 4 to 20 milliamp. There's a bunch of industrial control signals, but sometimes you're just going to have a customer and you know that if you leave it the way it is, that he's just going to screw that thing up. So you just place another resistor in line with it so they can never get below certain values inside of there. Sometimes you do this inside of software, other times you'll do it inside of hardware by physically placing this resistor in here. Okay, one last thing before we do the actual analysis on this. The drawing, once again, is screwed. This load needs to be whited out, and this load needs to be placed in this line over here where we're going to be able to actually control it. So I'm going to go and redraw this line over here, and then I'm going to go and draw this, and we're going to call that thing load. Oh, I don't know what's happening. Oh, wait, I think I got this. I think I figured out why it sometimes does strange and wonderful things. I think what I need to do is build a large white box, and then I can build a smaller as long as it stays inside. Ha! Got it. Okay. Perfect. So now we've got our load moved over, and I think I figured out this problem with why sometimes stuff jumps to the front. Back to what we're going to go and take a look at over here. This is now where it has been moved. A couple of things that have just happened over here. First of all, I want my control circuit not to have its current run through the load, because otherwise as I change my load, I change my control circuit. It's just going to be a problem for me. So I want to have the load only in line. If I take a look, the load is now only in line with the AC supply. It is not in line with any of my control other than the actual control device itself, which is going to go and be that triac that we see over there. Let's give ourselves a couple of polarities. We're going to go through this thing just in a positive and then in a negative direction. If I take a look at this, is a capacitor an AC device? Absolutely, capacitor is an AC device. And I'm going to be able to go and build a value of voltage across it. I'm going to send electrons down here. We're going to say that this is blocking initially, so we're not going to examine that one. I'm going to send electrons over. The electrons are going to start to build up on here, and as they do, they drive away electrons that are going to go out through here. As I build that value of voltage over top of here, eventually I'm going to go and reach a point where this diac is going to be able to go and break down. Now I'm going to go and have my diac voltage plus what I have for my voltage I need over top of this gate. Remember that this is still a PN junction inside of here. So you're going to need to have about 0.7 volts over top of there in this direction for us to go and build that, plus whatever my diac voltage is itself. So we can go and say that that diac is going to go and be, well, I don't know, let's say it's a 2 volt diac that I'm going to go and have, which would mean I need to have 2 volts plus 0.7 volts. So I need to have a total of 2.7 volts at this point. So my cap starts to build depending upon the amount of resistance inside here. It's going to take it a little bit to build all the way up to 2.7 volts. But when it hits 2.7 volts, this and this are both going to be forward biased. In reality, those two act. It just disappeared there. Maybe I didn't fix this. In reality, these two act as if there's two switches in series that are related to each other, and they're just going to go and close. Okay, I don't know what's going on with this load. This is driving me nuts. Weird. We will just draw it over top because it's derailing what I'm trying to go and do over here. Okay, there's my load. Deal with it. Doesn't look as nice as the other one, but that's just what it is. All right. Over here, we see that these two are going to be in line, and they act as if they are two switches. Once we reach the proper value of voltage for both of these, both switches are going to go and close. This 0.7 is going to be met. This 2 is going to go and be met. And we are now going to go and run current through there. What current is going to go and run through there? Well, if I take a look at it, I'm going to go and run off this current through there. Those electrons are going to leave from here because they can travel through here. They're going to go and travel through here, back through this. Remember, it can take current through in either direction to go and drop the value of voltage that's across there. Now, this thing over here, does it need sustained power on it? No, it just needs to have a pulse. So the very first time that this happens, boom, I'm going to go and have this that is going to gate itself into conduction, and we are going to be able to go and get bulk current through our load that is then going to go and travel through our circuit. So this is going to be when I've got the positive negative direction like this, and this little triggering action could actually happen a bunch of times because this is going to go and drop that. This is going to go and shut off here because we're going to go and lose those electrons, right? Those electrons and holes are going to fill. So this little bit of current over here is going to go and shut off at that point, and then it's going to start to go and rebuild. And so while this thing is going through the first positive alternation like this, we might have multiple little builds and discharges off here. Build, discharge, build, discharge, build, discharge. But really it's just where the first build discharge is that is going to go and trigger. I'm just going to draw that little build discharge here in the positive direction underneath here. That little build discharge, wherever the first one of these happens, is going to go and gate the triac, which is then going to go into conduction. So then we will be able to go and get all of this waveform through on my first alternation. We then go to our opposite side. This is now going to go and become my negative. This one's going to go and become my positive. If I did have some voltage built on here, like that and like that, what would happen is this positive over here, these electrons would just flee from that plate back there, and this one here would go and drive electrons through in this direction to fill those holes. So it's going to go and bring it back down to a net of 0, and then once it's brought it back down to a net of 0, it is then going to start to build electrons on this plate, driving electrons away on this plate. Once again, we need to go and have 2 volts and 0.7 of a volt for this one over here to go and turn this on. So as we're building now in this negative direction, Here's my negative sine wave. We are also going to go and have a negative sawtooth that's going to start to build like that. And whenever my first sawtooth hits its peak enough that it's going to be able to turn this on, we will then be able to go and drive the electrons. See, they're going through the opposite direction now. Now they're going to go and drive through here, but it's that first little pulse, that blip that we're going to get, that's going to go and turn this on, and now we're going to go and drive bulk current through in the opposite direction over here. So all we're doing is we're adjusting this resistance inside of here to adjust how quickly we build this little bit of voltage across here, and we get that first little blip. This is going to be oscillating in a positive direction, then it's going to oscillate in a negative direction, then it's going to oscillate in a positive, a negative, etc. But it's always going to be associated with the first blip, whatever that first peak is, then it's going to go and carry the rest of that waveform through. So we're going to be able to go and get that phase control of our actual load itself. These values, how long it's going to go and take, is all going to be done through here. If I move this bar down to here, let's wipe that section out, and if I move that bar down to over here, we're going to have more resistance in, which would mean that this sawtooth waveform that we would have would take a longer time to reach a peak. A longer time, which would mean that we would cut away more of the initial waveform, and we would have less power out. So we increase the resistance on here, we get less power out of our load. We decrease the resistance on here, we're going to get more power out of the load. It's a pretty cool little thing. And because it's very common for us to go and use both of these together, the diac that is going to go and give us the little blip with an oscillator, and then the triac, which is going to carry the bulk current, we'll often find these things that are going to be packaged together. We'll have these diac-triac packages that contain both inside of the same. Okay, next one that we're going to take a look at is called the UJT. The UJT is a unijunction transistor, and the name does not mean actual transistor, because transistors are able to be used in an AC format for amplification or increasing the amount of current. Tiny amount of base current results in a large amount of collector current, right? We've done that thing numerous times. What we have over here in the UJT is actually going to be a solid chunk of semiconductor, base 1, base 2, that we have over here, and then we've got this little emitter. This one over here, base 2, is going to simply be what we refer to as a reference terminal. It needs to be attached to a voltage so that we can go and reference everything else. And because this is semiconductor, it's neither a good conductor nor a good insulator, so it acts as if it were a resistor. Okay, a whole pile of resistance inside of here going across from one side to the other. We're going to get a small amount of current flow that is going to go through this thing continuously, and we need that in order to go and maintain conduction, and so we can actually hit this triggering point. Over here I see as well that I've got an N type of material and I've got a P type of material. We can go and build these as a N channel, or we can build them as being a P channel, but it's going to go and operate a little bit different. It's just going to go and have to reach a certain value before they can turn on and off. And where the UJT really shines is the fact that we are able to select the value of voltage. Diacs have to be built by the manufacturer. If I need something that breaks over at 5.3 volts, I need to go and search until I can find one that is suitable at 5.3 volts. Whereas my UJT, I can just go and buy one that's got a range across it, and I can adjust that range. Different cases, once again, going to be really small, size of a pencil eraser, if not smaller for them. Symbol over here looks similar to what we had for some of our FETs, except instead of an arrow coming straight in, we've now got it in on a little bit of an angle over here. And ratings of these things are going to be small. If you take a look at the dimensions over here, this is 0.3 of an inch. You know, it's a very, very small little package that we're going to have. Leads are going to be small off of these, etc. Once again, do not go and memorize cases and case packaging and stuff like that. That's something that later on, if you have one and you're certain that that's what you need to go and replace, you're just going to look up the part number and figure that out from there. Ratings on them are going to be small. Once again, looking at power, the amount of power that we can run through them, all these numbers over here are in milliwatts, which means that they're 1/1000th of a watt. So we're looking at a 0.45 of a watt or a half watt total as being our maximum that we could go and have. Not a lot, and definitely not going to be sufficient to go and carry any sort of bulk load. We're going to use these things in a lot of cases as a trigger to create a triggering device that we will then run off to a SCR or triac that will do the actual bulk current carrying for us. How do they operate? Well, inside of here, we're going to go and have something that is going to be called my intrinsic standoff ratio. And the intrinsic standoff ratio is going to go and be a percentage. It's really just going to go and tell us kind of what percent of the max voltage, the interbase voltage, this thing is going to go and fire at. We'll start by taking a look at this over here. And if I take a look, I've got this up over here, Greek letter nu, which is going to go and tell me what I've got for my intrinsic. Now note it's a range, about 0.54 to 0.67, because there is a little bit of error in manufacturing. And then I've got this other rating over here, which is called my interbase voltage. And the interbase voltage is going to go and be the maximum voltage that I can place across. I don't have to hit that voltage, but it is what I can place across it. I can go anywhere from there down. I'm also going to go and have a breakover resistance that's going to be rated in k ohms, so 4,000 to 12,000 k ohms for this one, etc. So it's a fairly high resistance type of device. What happens inside of here is that, remember how we said that it is made up of a solid block of semiconductor? Hold on, we got that picture right over here. We're going to be able to flow current through here. Now I see that physically this little piece over here, the emitter, is placed not in the dead center but higher up. The physical placement of this is going to go and determine what that intrinsic standoff ratio is going to go and be. Looking at this, they go and draw it out as if it were a set of resistors. And these resistors are going to be made up of basically the amount of silicon or semiconductor material that we are going to go and have going up this thing. Remember how going from the bottom, from base 1 up, there was a larger amount of resistance? We could go and say that this might be a value of 6k ohms. And then this over here might be a smaller value. It's closer to the top, 4k ohms. Kind of lines up with what we have over here. Less semiconductor, so it's a 4k ohm resistance from this point to this point. More from this point to this point, so it's going to be the 6k ohms. These values then are going to go and have voltage that's going to be placed across it. And as I place a voltage across it, I am going to go and rise until I hit a value that is called my intrinsic standoff ratio, or whatever it needs to be for this thing to go and fire over. Excuse me. Just losing my voice here a second. What we do with this is as soon as we exceed this value, here's 6 volts out of 10 volts, 6k out of 10k ohms, plus this actual PN junction, because we've got a P-type material that's embedded inside there, so we're going to have that small amount of depletion region, or barrier potential as it's sometimes called, that we need to overcome. We add that on top of there, so if I hit 6.7 volts, all of a sudden I would get conduction through this path from negative up to positive. But if this point over here does not reach 6.7 volts, if it's floating at a lower, if it's floating at 3 volts, it's not going to be enough to go in forward bias and drive through here, because 3 volts is going to be more negative than this point over here, which is at 6 volts. And so it's just not going to bias and drive forward. Placing them into a DC circuit over here, they show you an example where we've got base 1, base 2. We'll go and throw the same values off here. We'll call this one 4K. We'll call this one 6K. And we'll say that this is going to be 10 volts over here, which would mean that if I've got a total of 10k ohms going across here, we would be dropping a volt per k. So this over here is going to be dropping 4 volts. This section over here would be dropping 6 volts. Basic math. Not really electronics, it's just simple Ohm's law. You should be cool with that. Because we have got this thing embedded in a dissimilar block, there is going to go and be this depletion region around the outside, which means that we have to go and put that in as well. So it's a 0.7 volts for is what we say is our default for most of these. So that's what this section right over here is going to go and be, this little diode that they have. The diode is just representative of that barrier potential. And then we see that over here we have got another value of resistance that we are going to go and have. We can have a variable resistance. We can go and have a fixed resistance. This voltage that we have over here, as long as this voltage exceeds 6 plus another 0.7 that I'm going to go and have across there, I'm going to be able to go and drive this thing into conduction. And I would be able to go and at that point use this as a switch to go and drive current out and through this section over here. Here's how we go and change these values of voltages. We're going to go and place them in with, once again, our little old friend, the RC timing circuit. Let's go and apply a couple of values of volts to this thing. We're going to start with this thing at 10 volts. And we're going to go and say that because it's going to be 10 volts, that's going to be placed all the way across here. We're going to go and place that across from here all the way to here as well. We're going to go and have another resistor that's going to be placed in line with this. And then we're going to go and have an RC timing circuit that we are going to go and have. Now you can place this down over here, or you can place this one up top over here. More commonly, you'll see it placed up top over there so that this B1 terminal is referenced to the same as this cap, because that cap is going to be your control device. It's just poorly drawn, but it's not critical inside of our circuit analysis, so we'll leave it there this time. Same deal as before. There is always going to go and be current flow through here that we are going to go and see. And that's fine because it's a high amount of resistance. So I'm going to start by just establishing one path of current flow that is never going to go and change. And that's going to be this path over here from negative through this resistance through the silicon channel and back over to my supply. There will always be current that's going to be flowing through there. And because I times R equals V, I'm going to go and have volts that are going to be dropped across, the top section of my UJT, the bottom section of my UJT, and some volts that are going to be dropped across here. Let's say that this thing over here on the bottom drops a total of, I'm actually going to change my values here because it will make more sense. We'll call this 12 volts, and we'll say that, and therefore across this whole section, we would have to be dropping 12 volts as well. We'll say that this drops 2 volts, okay? Which means that this over here would be dropping the remaining 10 volts. And then across that, if we've got this thing biased at approximately 2/3, which is going to be common, it's a standoff ratio that's usually between 0.5 to 0.8, we're going to say that this thing is biased at 60%. So, 6 volts plus another 0.7 volts. So I've got 2 volts dropped over here plus the first 6 volts. That means I got to get to 8 volts plus I got to break over top of that junction. So I need to get to a value of 8.7 volts on here. Once I get to 8.7 volts, this thing is going to go and conduct. So what I'm going to do is I'm going to start to flow now my other path of current. So the blue path of current stays in here at all times. This one over here, we're going to go and build electrons on here, driving electrons away up here. And as we drive those electrons away, we are going to go and see this voltage starting to go build across here. This would be a variable resistor, so we can choose the amount of volts that we are going to go and see. And what we'll see is we are going to go and see this voltage that is going to go and grow across this cap until the voltage reaches this value of 8.7. And once it reaches this value of 8.7, boom, it is going to go and put this thing into conduction. All of a sudden, all of these electrons over here are going to be able to go whoosh through there and fill the holes on the top. So if I take a look at what that's actually doing, it's discharging this value of voltage that I'm going to go and see here, absolutely, but it's also sending a crap ton more current through this resistor. I times R is equal to V, which means that if I all of a sudden have got my red current and my blue current going through there, I'm going to go and see a spike in my voltage. And that's what we're seeing on this bottom line over here, is we are seeing the voltage that is going to be across here. It's normally going to be, steady, steady, steady. And then at the peak, when this thing goes and discharges, boom, we're going to go and have all that current that's going to go through, and we're going to get a spike, boom. These two graphs over here, by the way, are not lined up with each other. They should be better lined up. For some reason, we're missing this first sawtooth over here, which we could just draw in actually, and then it makes more sense. I'll just do that. It starts from 0 like that. So start from 0, built up, hit that 8.7 volts, which is what we needed to go and trigger into conduction, which then sent a blip of voltage through. And then we are going to sag back down to our regular, when this thing drops below its holding amount of voltage, the voltage drops below this, and all of a sudden we're no longer able to go and hold this forward. This drops off, and so then this is going to be back down to its regular 2 volts that it has across it, and then boom, we're going to jump all the way up, and then go back down, boom, jump all the way up. And so we have the sawtooth that comes out of here, as well as we have got this other one, which is going to be a spiky little trigger voltage over here. This whole circuit that we have up top here does not control, or does not actually drive any load current. Okay, this whole circuit that we're seeing over here is simply a trigger current. I can choose to go and take my trigger for my other device, and over here we are going to go and draw in an SCR, just because we can. Oh, I can't even draw a triangle this morning. This is terrible. So I've got my SCR over here, and I've got my main load. Stick a bunch of big zigzags because it's a big load that we have over there. And really, it's going to be my choice whether I want to go and attach this trigger device to here. If I do that, then it's going to go and have a low amount of voltage. It's got to be below whatever it takes to put this thing into conduction. But then every once in a while, when this thing jumps up, boom, it would go and push this thing into conduction. And then we would go and have, conduction through here. At that point, we would have to wait until we lose our holding current on the SCR to go and shut it off. So, maybe this circuit goes and shuts off or whatever. It doesn't work as well inside here because we don't have that automatic commutation of the AC. But all that we're showing off of it is the fact that we can select to either use this signal to a trigger, or we can go and use this signal over here to our trigger as well, which would be where we're looking for this peak over here. Gives us two different styles of triggering signal to go and pick up with. This is really a nice one. We like having this really rapid rise because this one over here, if it's a bit ambiguous, the level that it triggers at, it might trigger a bit here this time, and then here this time, and then here this time, and then here this time. So I start seeing having differing gaps, so my frequency doesn't stay as steady. Whereas this, it's much easier to go and have a high peak. That's because it's a rapid rise. It's going to be much better timed off of them. So UJT oscillator, sometimes referred to as my relaxation oscillator. Okay, last component that we have to go through out of these specialty thyristors is going to be my LASCR, my light activated SCR. And it is an SCR that is going to get turned on by the presence of light. I don't know how familiar you are with photovoltaics, but the way that photovoltaics work is that they are basically going to go and be a P and an N type of material. So we can go and take N type of material, we can take a P type of material. They're going to be really, really thin. N type of material has got an excess of electrons. P type of material has got an excess of holes. That we're going to go and have in between those two, we've just got ourselves a depletion region. Okay, it's a standard diode when we take a look at one of these. And what we'll do with that photovoltaic cell is we then expose it to sunlight. I've drawn one of these since elementary school. Shows, I guess, too, when I look at how bad that is, but whatever. The photons, which are going to be this weird thing, I don't know, I can't really describe a photon, most people can't, but the photons are massless particles that somehow do have mass at the same time, stuff like that. It's pure magic, but it's also science. Anyways, they come from the sun, that's the light, they hit this, and when they hit this, they actually excite, they actually cause impacts with these electrons, and some of these electrons are going to get bumped and just get yoinked right over top of that depletion region. And as soon as they get yoinked over top of that depletion region, then they're able to go and travel through an external circuit. This would be my load off my photovoltaic back up to over here because it is an N-type material. It wants to hold onto its electrons. A P-type material, it wants to hold onto its P-types over here. And it's just the sun that's knocking them through. And then they're like, ha, can't fool me, sun. And they go back to the other side. We've got the exact same thing inside of our LASCR. If we take a look at the LASCR itself, it is going to go and be an SCR, so we're going to have an anode and a cathode. We're going to have a gate that's going to be attached to it sometimes. Other times we won't have the gate. This one's got 3 terminals, which means it's got a gate terminal. Some of them will not have that third gate terminal off of it. And they're going to have a lens, and we're just going to go and create a small amount of voltage off of light hitting it. It's a small photocell combined with an SCR is all that it is. We combine it with it, and then it's going to go and drive electrons through. It's going to go and turn this thing on. Lenses are going to have to be visible. Now, they do work better with infrared light than they do with visible light, which means that they're really handy for places where we don't want to necessarily have visible light. We'll use these in a lot of optical isolation or optical controls where I've got an area that's going to be, something that I want to keep safe. Let's go and call this thing the computer brain. We'll call it an industrial computer called a PLC, Programmable Logic Controller. This is the brain of it, so we want to keep that safe. Okay, you guys could all operate with the loss of a hand. It wouldn't be awesome. You'd like to get a prosthetic or something like that, but if you lose your hand, you'll still be able to go and survive. If you lose your brain, your body shuts down. It's just, the rules of it. So inside of our PLCs, we're going to have the same thing, and then we are going to go and have the I/O, or the input outputs that we're going to go and have. That I/O is going to be coming in from electricians' carry field wiring. So you guys are out there doing who knows what. Here's some voltage. We'll just apply that over here. I don't know. We'll just attach to this terminal over here. You do all this crazy stuff to our I/O cards, and when you do that, you sometimes screw it up, okay? And when you screw it up, what's going to happen is we don't want your electrical screw-ups. You know, let's say you took 600 volts and attached it to a 24-volt card. We don't want all of that 600 volts to travel through and affect the brain of the PLC, because that's going to go and screw the entire thing. We'd rather that you just blow up the I/O card. And so what we'll do is we'll use this system called optical isolation, where your I/O is simply going to be attached to a bunch of small infrared diodes inside there. Those diodes are going to generate light, and then that light is going to go and get picked up on the other side by, oh, you guessed it, a Lasker. See how we have that over here? We've got that, and so that means that if you have crazy terrible electrical on the outside of your system, you're going to blow up the I/O card, but the I/O card itself has no physical connection to the brain. Everything is done through light. We call this optical isolation. It's an air gap of sorts between the one side to the other. So crazy stuff can happen on the outside, faults or poor wiring, but it's not going to go and affect the brain of the PLC. Some cases you can go and adjust the sensitivity of these things. Remember that I said the thing that sees the light inside of there is going to go and be a photocell, or what we often refer to as PV. Photovoltaics is what PV is short for. The photovoltaics generate voltage. Now I can go and allow that voltage to drive in to my gate to go and turn this thing on. Or if I want, I can bleed off some of that voltage through an external circuit that they're showing over here. And if I do that, if I bleed off some of that voltage, it's going to go and affect the level that this thing is going to go and trigger at. So I basically get an adjustable, the amount of light that I get is now going to allow me to go and choose when I'm going to go and fire this thing on. So we'll have this trigger adjust. We'll use that to adjust our levels just by bleeding it off. If I go and move this to the top over here where there's like almost no resistance, we would be bleeding almost everything off this photovoltaic. And so we would need to go and have a huge amount of light coming into it to go and gate this thing on. But if I go and adjust it in the opposite direction over here, and I take this thing all the way down to the bottom over here, then we're going to have maximum resistance inside of here, which means that we're only going to divert a tiny bit of current, which means that we only need to get a little bit of light into this thing to go and turn it on. Excuse me. Laskers themselves are going to be control components. They're not going to be bulk current carrying components. It's not like you're going to go and grab one of these and be like, hey, it'd be cool to have a heater that I could turn on and off with a flashlight. You're not going to just stick a single Lasker inside there, because they are going to be limited to, most cases, small values, an amp or under. Sometimes you can go higher. They do go wattages almost up to 0.5 kilowatt, somewhere in anywhere between the 300 to 500 range is where we'll commonly see them, but it's not going to be large amounts. What we'll use the Laskers for, in a lot of cases, we'll use the Laskers to go and fire a larger SCR triac that will carry our bulk current. The SCRs and the triacs are your heavy lifters in all cases. These other ones here, they're just there to go and give us control. Okay, that's your specialty thyristors. On to learning task 7.